All right, so I'm going to talk about the topic Darwinian medicine, also known as evolutionary medicine. Now, this isn't just like let a disease or illness run its course and only the strong survive. That'd be messed up. And it's also not alternative medicine. No, it's just a different perspective. It's just applying the evolutionary perspective to the field of healthcare and our understanding of disease. So what I mean by that is in typical health education and healthcare, they really focus on how these diseases happen, what's breaking down in the body, what protein is missing, and so on and so forth. However, a Darwinian perspective, or evolutionary perspective, more looks like at why that is happening. Why are humans more likely to suffer from this affliction? Why is this disease more common now and increasing in prevalence when it was virtually absent in the past? So when you think of the Darwinian medicine in general, it really breaks down to three sort of fields that sort of encompass this lack of an evolutionary appreciation to health and disease. That first category, or that first sort of field within Darwinian medicine, are that symptoms are often adaptations. Sometimes they're unpleasant, but they're adaptations nonetheless. For example, fever, when you develop a fever in response to illness, that's actually adaptive. Your body's doing that deliberately to try to limit the spread of that pathogen inside of you. Pain, as we've mentioned in a previous video, pain is extraordinarily adaptive. It really prevents your body from suffering harm, despite it being painful and harmful. The other major category of Darwinian medicine is a lack of appreciation that we're often involved in these evolutionary arms races with the pathogens we're trying to get rid of. So if you think of antibiotics, antibiotics are fantastic. They've saved countless lives. However, antibiotics, on the other hand, evolutionarily simply select for resistant bacterial strains. So yes, it does mitigate infections on individuals without a doubt, and again, save countless lives. However, it is also basically a practice of producing resistant bacteria at the same time. Same thing with cancer treatments. It's the same idea, killing the vulnerable tumor cells, often leaving or favoring these tumor cells that are resistant, which is why subsequent treatments typically fail. And the third field, basically approaching the third field where Darwinian medicine kind of steps in from this evolutionary perspective on disease, are with evolutionary mismatches. The notion of an evolutionary mismatch are that traits adapted for one environment will be maladaptive if expressed in the wrong environment. So a classic example there, or if you think of little sea turtles, right? These little babies have to figure out where to go, when they first hatch. They don't have anyone kind of pointing it out to them. So these brilliant adaptations to point them where to go. The first is that they follow the sounds that they'll hear. And what other sounds would be out there in the natural environment that would be louder than essentially the crashing waves of the ocean right there. Also, they follow the light. So where else would the light be coming from in the natural environment? From the night sky, if it's going to be reflecting off of the water, so they can follow that. So basically with these two cues, along with these adaptations, they just follow the sight. They follow the sight and they follow the sound, and they invariably end up in the ocean. That is, again, works flawlessly in natural conditions, which is why it's basically ubiquitous amongst these sea turtles. However, if you throw a bar up across a street, after humans move in, then the sea turtles are going to pop up and go, oh, well, I'm going to go to the bar instead. It's not because they're little alcoholics. It's just simply that that's where the sound is coming from. That's where the light is coming from. So again, they're expressing what are normally brilliant adaptations under natural conditions. However, these are extremely maladaptive in the modern environment. And these conditions, or these mismatches, are actually probably the leading cause of our death and discomfort nowadays. So they're of particular importance. So anyway, I'm just going to dive into each of these three categories in a little bit more detail. So the first major, sub-discipline of Darwinian medicine, it tackles this lack of appreciation that symptoms are often adaptations. A lot of symptoms are, unpleasant, obviously, but they're also adaptations. Again, despite these things not being something you like to go through doesn't necessarily mean they're not adaptive. So for example, pain, we talked about that in great detail in a previous video. Pain is adaptive.
So pain, although inherently unpleasant, is highly adaptive because it draws our attention to stimuli that are harmful and detrimental, and functions to motivate response to alleviate that harm and to reduce pain. So drawing our attention to a painful stimulus, having behavioral modification to eliminate or alleviate pain or harm from that stimulus, which also functions to promote associative learning thereafter, to reduce certain behaviors into the future that might lead to painful outcomes. So pain is really, really adaptive in that regard.
All right, next you could think of fever. Fever is actually another very unpleasant situation to be in. However, fever is adaptive. Your body increases, basically sets its thermostat higher to kill or to hinder the growth of whatever pathogens are inside of you, so you can have a better time at fighting them, or a better advantage at fighting them. So if you fight against that fever, it actually could be counterproductive. Also inflammation. Inflammation, again, it's always kind of tied to some sort of negativity. However, inflammation is an adaptive response of your body to try to contain essentially any kind of infection or breach in its defenses. Just think, if you get bit by a mosquito, right? It's going to dump out its whatever compound it puts in there to anesthetize you from any kind of pain, anticoagulants, what have you, are going to be in its saliva. So your body's going to react to that and have an alert, and that's going to cause a lot of the increased blood flow to the area, which is why it turns red, and it swells up because you have a net increase of fluids in the area, and also you have a lot of immune system cells going to that area to try to contain that. You always have the breach in the security over here, so you really need to rush and contain that. So these are adaptations to, again, prevent or to fight against pathogens, which is why it's not surprising when individuals that are suffering from certain viral infections, when they take acetaminophen, which is a fever reducer, so antipyretic, and also an anti-inflammatory, those taken together actually can exacerbate symptoms and actually promote the spread of some infectious disease. So symptoms are often, again, adaptations, particularly the unpleasant ones. Another actually really sort of famous example that happened a few generations ago, it revolves around this drug, thalidomide. Now, this drug was widely prescribed in response to morning sickness. And that's when pregnant women just kind of have these bouts of nausea and vomiting. Now, it was obviously just at face value, individuals would say, well, these individuals are pregnant, these women are pregnant, they should be eating more, they shouldn't be vomiting. So we need to stop this. So this drug was widely prescribed, and it resulted in these birth defects, and it struck tens of thousands of children. So what had happened is this drug Again, it relieved nausea, but as a result, it also had this toxic effect on the limb buds for during elongation while the fetus is developing. So essentially, their limbs wouldn't elongate. So they were called flipper babies because essentially, they didn't have elongated limbs, just sort of these hands and feet kind of sticking off their main body or their torso. So that was obviously really bad on a number of levels. For one, the drug was in itself toxic. It didn't cause these effects through inhibiting morning sickness. It was just toxic. However, the reason that drug exists is because of our lack of understanding that you actually don't want to necessarily prevent morning sickness. It actually is an adaptation. So let's talk about that for a little bit. So again, morning sickness is actually ubiquitous across cultures. It might be more prevalent in some than others, but that tends to follow sort of adaptive reasoning. But it's the association between morning sickness and some sort of obvious factors of the natural environment which really sort of bring its adaptive value to light. Now think, humans have an extraordinarily broad diet. You can have individuals from different parts of the world having zero overlap in what they eat. And that even counts ancestrally. You eat what's available to you and around you. And part of our evolutionary success was because of our extraordinarily broad diet. But those also include some potentially harmful things, some toxic things as well. But they're not going to be harmful to, say, you as an adult, but they might be harmful to, say, a developing embryo inside of a pregnant mother. So, because things might not necessarily be toxic to you as an adult, you can have this broad diet, but you should really scale that diet back down to just a safer foods when it comes to pregnancy, because again, some of those things could actually be toxic to a developing fetus. So it makes sense that females, once pregnant, should have a heightened sensitivity and aversion to potentially dangerous food items. So that's what you tend to see, actually. And again, some of these associations were really discovered and brought to light by Paul Sherman. And he pointed out these associations where morning sickness tends to really decrease around 18 weeks after pregnancy, or after the first 18 weeks of pregnancy, and that's when the baby is less vulnerable to toxins when the mother is consuming. Don't let that be an excuse to go get drunk at the 18-week mark. But the idea is the fetus is less vulnerable to toxins then, so the mother's sort of sensitivity to those things and aversion to those things tend to decrease around that time. Also, foods that reliably induce morning sickness also tend to be associated with plant toxins. Think of spices and seasoning. These are actually plant toxins. Even coffee. Again, caffeine's a plant toxin. It's not there for you to enjoy it in the morning. It's there to basically deter herbivory from insects and the like. So ultimately, these things again aren't dangerous to you as an adult, but they do have toxins and they'll reliably induce morning sickness. Meats, strong tasting vegetables like the mustards and so on. Those again, plant toxins. Meats, they tend to can host parasites. So again, a lot of these strong tasting foods will also again reliably induce morning sickness. And again, it makes sense. Another association is that females that experience morning sickness or stronger morning sickness, more pronounced morning sickness, tend to have fewer spontaneous abortions than women that don't experience morning sickness or experience morning sickness to a lesser degree. So again, symptoms are often adaptations. And just like you don't necessarily want to disrupt adaptations such as pain, which you talked about before, you necessarily don't want to disrupt adaptations such as morning sickness. So in this application or when considering human health and disease, we should really be asking the question not only how are these things happening, but why? Why are these things happening? And that simple question of why do we tend to find morning sickness across all cultures around the world. Why is that? Is there some adaptive value to this before we try to immediately stop it? All right, so the second major theme, or the second essentially gap that evolutionary medicine tries to address, are that often when we try to treat diseases, we're just engaging in an evolutionary arms race. And we're often unaware of that and therefore unprepared for the consequences, which are typically disastrous. So what an arms race is, we should all kind of know what an arms race is, but just think simply, if you have two tribes competing against each other, one has spears, the other one develops bow and arrows, then okay, well, now you have to develop something to counter that. And then let's say you develop guns, and then this one develops, I don't know, tanks. It just keeps going back and forth. As one changes to adapt in response to the other one is going to, again, follow in suit. We're used to this with predator and prey dynamics, which is very obvious in predator-prey dynamics, where the prey that are more vigilant and aware and can run away faster and detect predators quicker, those ones are going to survive and reproduce more so than the unaware ones. So that's the predator exerting tremendous selection pressure on the prey to be more vigilant, more neurotic and flee faster, be more high-strung. But the prey also now are going to, in turn, exert a selection pressure on the predator. Because now the predator has to be more cunning and faster to try to circumvent those adaptations. So that's what I mean by arms races. So the same thing really applies when it comes to our treatment of disease, particularly when we're trying to combat bacterial infections, as well as when we're trying to combat cancers. So with bacterial infections, that is quite literally a practice in evolution every single time. So you have a bacterial population inside of you that you don't want there. You take an antibiotic which kills the vulnerable ones. That's going to overall cause the entire population to go down. It's killing a whole bunch of them. However, the ones that remain are going to be disproportionately populated by individuals that are resistant. So you take this antibiotic, it hits this population because of the overwhelmingly large diversity of bacterial cells. Some of those individuals are going to have just a natural random resistance to whatever you expose them to. So all the other individuals are going to essentially be exterminated or knocked down, and these individuals are now going to flourish in these conditions. So now you take the antibiotic again, it's going to knock the population down, but not as much because there are less vulnerable individuals available and there are more resistant individuals. So you're going to have less of an effect of weakening that overall population. And now as a result, you're going to have proportionately, again, more of these resistant individuals. And then again, you take it another time, and again, you're just wiping out fewer individuals now because now the population is going to have greater and greater frequencies of these resistant individuals. And then now you're just left with a population of resistant individuals. So the more, if you take this antibiotic in the future, it's going to have no effect. So that's a problem because ultimately, again, it is evolution in practice, and you can actually see measurable results almost immediately, considering bacteria's generation time literally only takes a matter of minutes. So the vulnerable ones being killed, the resistant ones reproducing at a greater rate, therefore increasing in frequency, can happen very, very rapidly. So how do we kill this pathogen, this enemy, that has such an ability to evolve in response to anything we do? Well, it's problematic when you just use something that's going to target and kill vulnerable ones because it's going to invoke the response to selection. The same applies for the application of, say, pesticides. Yeah, you apply a lot of pesticides to keep these maybe insect pests off your crops, and you will knock down the number of pests and the insects that are currently invading your crops. But again, you're going to be increasing the frequency of these resistant individuals. So over time, the effect of knocking down the population is going to become lessened and the relative proportion of resistant individuals is going to increase. So again, the same thing applies. And also the same thing applies for even cancer treatments. You shouldn't really consider cancer as being these clonal populations of these renegade cells that take over your body. I know it's a very, very diverse population that had to evolve around many, many roadblocks, from detection of your immune system to all these natural safeguards for these cells to be able to reproduce unrestricted. When you take something like chemotherapy, you just simply kill the most vulnerable cells in your body, the weakest cells in your body, which tend to be the ones that are replicating the fastest, which are the faster growing of these cancerous cells. So you kill them, but at the same time, so you're reducing the amount of cancer cells in your body, yeah, but you're actually also increasing the relative frequency of resistant ones. So you'll see an immediate, benefit, beneficial effect, but that effect will become less and less over time until it's actually no longer doesn't work at all. And that's why sometimes individuals that again survive the first bout with cancer, when it comes back again, those same treatments will not have the same effect. So that all being said, how do we do this? Because antibiotics are responsible for saving more lives than any other invention you could think of for humans, except for maybe fire. But ultimately, how can we have an effective approach to combating microbes, but not sort of be running into this inevitable problem of producing these resistant strains? Well, one is to actually use evolution to our advantage, because they are going to evolve in response to whatever we throw at them. But can we actually nudge them to evolve in a direction that's actually more beneficial for us? So for that, to explain that, let's talk about, or let's consider what happens when you have bacteria sort of enter your body. So bacteria will obviously enter your body, and that could be an ideal environment for it to take off in. I obviously already have bacteria living inside of your body. I mean, it's a pathogenic bacteria, a dangerous one, gets inside of your body, like an infection, and it could spread because it has a lot of resources available to it. There's sugars and all sorts of things. So there's a few ways your body tries to combat this. One is by starving them of certain limiting resources. So yeah, if food and water is unlimited, unrestricting of growth for a population, but they also need something like iron to grow, then yeah, you don't have to reduce access to, say, the sugars in the water, but if you completely reduce access to, say, iron, that limiting resource, that could essentially inhibit that population from growing at all. So that's what your body actually does. It will sequester iron, so your iron levels will go down when you're suffering an infection. Ironically, a few generations back, when individuals would get sick, doctors would notice low iron levels, get an adaptation, and prescribe, say, hey, you should take more iron. Although that's something you should really do. You're sort of circumventing an adaptation from your body. So anyway, it's called nutritional immunity, where your body tries to sequester, again, iron away. So bacteria are going to just try to get better access to this stuff. So one of the ways they do this are by releasing this compound, which we consider a public good. So it releases this compound referred to as siderophores. And these siderophores have an affinity for iron. So this bacteria cell will just make this compound at a cost, release it out to the environment. That compound will collect iron, return back, or be able to be collected back by a bacteria. But any bacteria can now take that in and take the iron. So individuals that are producing these siderophores are providing a public good to all bacteria, whether they're producing the siderophore or not. They're benefiting from all these extra sort of iron scavenging molecules that are out there. But now you have a bit of a social dilemma sort of arising amongst the bacteria. For example, let's say we have a diverse population. Let's say we have, these little guys, some limes and some rocks here. And let's just say that the limes are the bacteria that pay a cost and produce these siderophores. and the rocks are ones that benefit from siderophores that are coming in, same as the limes, but they're not producing them on their own. So collectively, they all do well if you have some individuals that are producing these siderophores. But if you compare fitness directly between the individuals that are paying to produce this stuff, whereas they're both benefiting equal from this stuff, that net cost is going to reduce their fitness compared to these individuals. So while they're both benefiting equally from siderophores, these ones are paying the cost of producing them, and these ones can instead, say, invest into reproduction. So if we sort of fast forward to the next time step, we'd imagine that the selfish individuals, the ones that are not producing siderophores, will be out-reproducing, will become more common, let's say, than will the cooperative individuals that are producing the siderophores. But overall, again, as a collective, they're going to do better in this infection. But this is this is a regularity that you can actually take advantage of. So what if we can exploit that difference? What if we can exploit that these individuals are essentially parasitizing, they're essentially social parasites on these individuals? Can we exacerbate that difference? So that's actually been investigated using gallium. So gallium is an element similar to iron. It behaves similarly to iron. So when these bacteria are producing these siderophores to gather and collect iron, instead of getting iron, it's bringing them back gallium. Bacteria is like, I can't use gallium. So what's going to happen if you flood this individual or get an individual that's sick and currently has an infection that's spreading, and you flood them with, say, gallium, then you'd imagine that the whole collective is not getting iron that they need to. So ultimately, the entire population is going to reduce in size because they're essentially starved iron. But who are going to be the ones that are worse off? Well, it's going to be the ones that are still paying the cost of producing these siderophores. So now they're all doing worse. So they're all essentially dying off due to this lack of iron, or they're all growing slowly. However, these ones are going to be proportionally worse off. So you're going to essentially be left with just these non-siderophore producing ones. And that's what you'd like to deal with to begin with. So the population does respond to selection, but it doesn't respond to creating a more resistant population that's more difficult to get rid of. They respond by actually becoming an easier population to deal with. You're essentially destroying their ability to work as a team. So really kind of a clever experiment. So what they did is they tested this out in waxworms. So they got these little waxworms sick, essentially, with a pathogenic bacteria, and then they injected some with gallium, they injected some with a control, and they injected some or treated some with various antibiotics, as well as a cocktail mixing antibiotics. And they wanted to look to see how were these various treatments affecting the growth of bacteria within these sick individuals. So if you look at the relative growth rate of bacteria, you'll see that it does get knocked down, basically, regardless of what treatment they're given, antibiotic or gallium. However, how effective is that over time? Can the bacteria evolve resistance to that problem, and how quickly? So in these treatments, they administered, again, gallium at either low or high doses, and they administered it in continuously or periodically, and then assessed the growth rate of bacteria over time. And you can see that the bacteria never actually changed in growth rate. Their growth rate was reduced and it stayed flat the entire time. The idea is if that curve or that line bumped up a little bit, it would show that the bacteria actually are able to survive or find a way around this. When you compare how it behaved with the antibiotics, just individual antibiotics, you can see that, yeah, even at low and high doses, it did knock down the bacterial population. But after just a few days, the bacteria started growing quite rapidly, almost unaffected by by the antibiotic. And you could see here where it was effective initially, but resistance almost started immediately. And even when you mix together and make a cocktail of different antibiotics, you could still see that resistance does evolve. It just takes a few days longer. So again, another kind of brilliant solution where it's not just giving up on antibiotics, but just having a novel approach to antibiotics. Now, another area you see this research again is with cancer. Cancer, surprisingly, or not surprisingly, are just the same kind of sort of social populations that sort of attack you via somewhat teamwork. Cancer cells, let's say you have a tumor is growing inside of your body, and it could do fine if it's a small little tumor. Again, these cells are growing very, very quickly. They need fuel to grow quickly, so they're going to take the sugars out of the fluid that they're being bathed with, this interstitial fluids, how the rest of your cells get stuff. They're going to get it that way. They're going to get their oxygen that way, and so on and so forth. But as this tumor sort of grows in size and becomes sort of more dense and populated with cells, then no longer is that simple diffusion going to work. This larger tumor needs a dedicated resource. So what ultimately is going to happen is it's going to encourage blood vessels to grow towards it and feed this collective. And that does so, it achieves this by releasing angiogenic factors. So angiogenic factors induce angiogenesis, which is basically the growth of blood vessels, the new growth of blood vessels. So when you're a developing fetus, that's why you don't have the same vein patterns everywhere in your body, because these things grow in response to where it's needed. So when you're a developing fetus, certain tissues that are relatively low in oxygen are saying, hey, we need some oxygen. They release these angiogenic factors, and then it encourages that blood supply to be delivered to that area. So essentially, one of the adaptive steps that cancer needs to take or needs to experience in order to really take over the body, again, it has to evade the immune system and other sort of cell regulating mechanisms, but it also basically has to get its own food supply once it becomes very large, or its own resource supply once it becomes very large. So it has to. So what happens is you have this mutation where if this tumor was small and didn't have that adaptation, essentially that mutation to provoke angiogenesis, then that tumor would eventually starve out or metastasize, but it would probably just starve out. Now, once this tumor gets, again, evolves the ability, let's say, to now release this compound, these angiogenic compounds, now this individual mutates or acquires this mutation, so now it's releasing this angiogenic compound. It's going to now feed this tumor, which is going to increase the success, again, of the overall tumor. So as a collective, they're going to do quite well. These individuals are going to reproduce. The other guys are going to reproduce, and everyone's happy, ultimately. But if you look within this specific tumor, well, then the ones that are not producing this angiogenic compound, again, they could reinvest those resources elsewhere into, say, reproduction, whereas these individuals are investing in this overall public good. A clever way to try to combat this was the use of anti-angiogenic factors. And the one that was a subject of study in rodents is endostatin. So endostatin is a very powerful anti-angiogenic factor. So ultimately, if this tumor is, again, releasing these angiogenic factors, then endostatin essentially render it inert. Just think of it just like the gallium with the siderophores. So this tumor now does not have the requisite resources it needs to keep feeding itself. So ultimately, the cells are going to start dying off. But which cells do you think are going to die off first? Which ones are going to be most vulnerable? Which ones have the greatest cost within this tumor? Well, the ones that are producing the angiogenic factors, because they're essentially all were benefiting equally from this, but these were the ones paying the cost. So now none of them are benefiting, but these ones are still paying that cost. So these ones should be selectively removed through that treatment of endostatin. So what they did to investigate this is in mice, they had mice that were predisposed to a few different types of cancers. There was a fibrocarcinoma, melanoma, and lung cancer. And they basically encouraged these tumors to just grow inside of these mice, and then they would hit them with endostatin and let the tumor shrink way down. But they wouldn't keep the treatment going to exterminate the tumor. They would still allow a little bit of the tumor to remain, and they would back off the treatment, let that tumor grow back, hit it again with another round of treatment, shrink it all the way down, but don't get rid of it entirely, don't drive it extinct, let it come back again, and just keep repeating that. Now the idea with that sort of serial application is if you knock down that tumor and kill the vulnerable ones, leaving the resistant ones behind, allow that to grow back again, that tumor should have a greater proportion of the resistant ones now than it did before. So when you hit it again, it shouldn't respond as strongly because there's fewer vulnerable ones left. So the effect of that treatment should diminish over time. And so you shouldn't really see that effect. So they tested this in over 2 iterations, 4 iterations, 6 iterations, and it was successful at reducing the tumor each time. So it was a really, really remarkable study. And that's why also it's common, or it's part of a lot of cancer treatments. So you can see here, again, we're not calling, the Darwinian aspect is not calling for some kind of completely, overhaul of the medical industry. It's just simply saying, how can we use evolution to our advantage in some of these treatments? And that's also why, in a different spirit, they're trying to engineer viruses that'll proportionally attack or go after just the cancerous cells, or find ways of educating the immune system so it can actually adapt and respond faster to some of these pathogens. So evolution is really all over in this field, again, but this is right here it's highlighting how it can play a role in these sort of back and forth coevolutionary arms races. Okay, the third main area where Darwinian medicine actually steps in due to this lack of appreciation of evolutionary consequences or evolutionary considerations with regards to our health and disease are with evolutionary mismatches. Now this is a really interesting topic, and I alluded to the sea turtle example earlier. But this is interesting because we are more likely to essentially die and be just sort of agonized from evolutionary mismatches than really any other causes of disease. So again, when evolutionary mismatches, it's that an adaptation for one environment can be completely maladaptive if it's expressed in a different environment. Or basically, if you evolve to suit one set of environmental conditions, it could be very, very different. You could be completely mismatched with a different environment. So an example I like to consider with regards to even humans are with goldfish. So imagine you have a little goldfish in a little goldfish bowl. If you just keep throwing food in there, that goldfish is going to keep eating and eating and eating until it basically just dies, until it bursts. And you might think, well, what a stupid goldfish. But no, not really. It's just never evolved. It's never experienced conditions like that in its evolutionary history where having adaptations of restraint, just saying, whoa, there's too much food there. It's never been in a situation where that decision is actually the beneficial decision to make. It's always evolved in circumstances where there's not enough food, so you need to just monopolize and take advantage of as much as you can at any given sitting. Again, if you just compare the two scenarios where there's too much food and therefore mechanism of restraint should help that organism survive in that environment, or there's not enough food and mechanisms of exploitation will help that organism. Clearly, this is what it's had to deal with its entire evolutionary history. So it's just expressing these adaptations just in the complete wrong setting. Now, same thing for humans, except for we're not just a goldfish, we're the one that's also adding food to the goldfish bowl. And again, it makes sense because when you're hunter-gatherers, we needed fat. You need fat to power you on your long persistence hunts or gathering expeditions. And you need to have, again, you need to have the energy between meals. You don't get to wake up, eat a nice hearty breakfast, then go after your food for the day. You need to have some reserves to power you through that. Also, we have very large and very costly brains. Our brains are about 4 times more costly per day than, say, a chimpanzee, which is also a very smart animal. So these incessantly costly brains need constant supply of energy, needs constant sugars. If it's even without that for just a matter of minutes, you'll have permanent brain damage. So our body accommodates by having fat stores. So naturally, we are supposed to be a fatter primate relative to the others to accommodate, again, these things. So it's obviously extremely important that we have enough fat, because not having enough could cost you in reproduction, and it could cost you directly in your ability, again, to survive right then and there. And that's also why, if you think of with human females, if their body fat content goes too low, they'll actually have this thing called exercise-induced amenorrhea or hypothalamic amenorrhea, which is basically when their body fat goes too low, the reproductive system kind of shuts down. They don't experience their periods, because having too low of fat is detrimental to your reproductive success and your survival. But it never was the problem ancestrally that there was too much food, and those that were like, it's too much there. It was never a case where they actually had an adaptive advantage. So again, just like the goldfish, you shouldn't expect them to evolve mechanisms of restraint. You shouldn't expect us. You should expect actually the opposite. Individuals that craved fat more, that were more motivated to go on those hunts, more motivated to go after food, more motivated to eat all the fat that they could find, those individuals left more descendants than individuals that were like, nah, that's good, I'm on a diet. So ultimately, it makes sense that obesity would be the largest issue in modern human health because, again, we are completely mismatched with this environment. We have the cravings for fat to get these calories, but we don't have to exert the energy to satisfy that as we did in the past. So that obviously is the leading cause of death, or related to the leading cause of death, which is heart disease. Reproductive cancers increase with obesity, causes inflammation internally in your organs, which increases the risk of cancers as well. And also metabolic disorder, type 2 diabetes, and so on and so forth. So clearly, obesity is a direct mismatch, a direct result of an evolutionary mismatch with this modern environment. Another major evolutionary mismatch with this modern environment actually has to do with the development and maturation of our immune system. And these basically together really kind of encompass the modern diseases, obesity and immune system dysfunction. So the immune system is an adaptive machine. We call it a Darwin machine. It's a learning machine. It's fantastic. Just imagine our generation time is a couple decades. The generation time of a virus or bacteria is a matter of minutes. So how could we possibly engage in even stand any chance in an evolutionary arms race? Well, it's because we have a system, our immune system, which actually has a very short generation time of cells. So we produce a huge variety of cells. Those that are effective preferentially reproduce. Those that are not, do not. So ultimately what's happening is you're kind of having this Darwin machine sort of chugging along that can respond dynamically to these threats that are constantly evolving. So really cool. But another aspect of our immune system is it has to kind of figure out not only potential problems it's never seen before, as far as the flu virus that you haven't got, or this novel coronavirus, which is currently running across a few countries right now. has to be able to understand these things or figure out how to resolve these things before it even sees it. And that's actually one of the benefits of vaccines. So what happens is your body produces cells completely randomly. And if you are exposed to a flu virus that you've never experienced before, let's say polio, one of these cells are going to figure it out, bond to it, and say, I know what this thing is, and only I can identify and kill this thing. So that cell is going to clone itself a whole bunch of times to sort of build up this assault force to then take this out. After it's fully taken out, then then part of that assault force already becomes dormant, and next time that thing shows up, it's not just a few individuals that are excited at this response, but you have a whole sort of dormant army that can just immediately start attacking, and you're also starting at a greater position of cells that can essentially do the same thing. So if you do get polio or Ebola or this coronavirus, for sure, you're going to have an evolved response almost immediately. It's just whether you're going to be able to have a sufficient force to fight it before you have permanent damage or die. So what happens with, say, vaccines, you get that exposure the first time. So now, if you do get it, so if you got exposed to the polio vaccine, you got exposed to that virus in a non-harmful way, so you're able to build up sort of this assault force. So if it ever shows back up again, you have more of an immediate response. And that's, again, the idea of vaccines. You give someone an attenuated virus that's not going to be harmful to the individual, but the body essentially gets a trailer, gets a preview of what it might be up against. So that's one of the brilliant adaptations of the immune system. But the other one, again, is that your immune system has to figure out where you are and what to ignore. So it has to figure out what to attack and also what to ignore. And those are intimately related. Because things that are part of your normal environment, even if they might not be beneficial for you, you should still learn to maybe ignore them because it might be more energy effective for the individual. And also, humans are a global species. Before our specific species even popped up, Homo erectus occupied many different continents. So the immune system has to be able to respond to novel threats. It also has to respond to being able to be tolerant of novel environments as well. So ultimately, it's kind of similar to how individuals learn language, is how your immune system learns about its surrounding environment. So if you're a little baby, you obviously can't speak, and at least for the first year, but it's still important for you to hear crucial sounds, because you evolved adaptations to learn and use language. You didn't evolve adaptations to learn and use English or Mandarin or Spanish or French or German. No, you just simply learned, you just simply have adaptations to learn language in general. So what happens is your body or your brain picks up on what individuals are speaking around you, and those sounds, the vowels, and it specializes on those. It goes, that's the language I need to learn. Those are important vowels. Those are important sounds. I need to be able to decipher between those, maybe even subtle sounds. I have to develop a sensitivity for those, because that is what's going to be my normal environment. And then eventually, as you're building your brain, you're setting in that architecture from very, very, very young. Your brain continually grows, until you're about 7 years old. So ultimately, even before you even speak the first word, if you deny that baby access to human speaking, it is going to have impaired language skills the rest of its life. Again, even though it couldn't even speak during those times or make any sort of sense during those times, because it was, again, setting up the architecture of these are sounds that are important for me to be able to decipher between. And that's also why, if you've only learned one language in the household growing up, and then you start hearing someone speak a different language, it sounds like they're saying the same thing over and over again. You can't decipher those subtle differences, because ultimately, you can't hear them. You don't have a sensitivity to them. So when you speak, you make those mistakes, hence giving you an accent. So these things can last, obviously, a very, very long time. And the reason I bring up this example, again, is we're all familiar with it. So your brain, it has this general purpose communication, computer going on in there, but it still has to build part of its architecture based on what it assumes are going to be regularities for the rest of your lifetime. So same thing as what your immune system does. It goes, okay, what am I dealing with is going to be normal in my environment, so I can just learn to sort of normalize to those things and worry about the things that are actually a threat. So how does it figure these things out? Well, your immune system doesn't have little eyeballs to pop up and go, oh, okay, well, there's these plants here, and there's that kind of pollen, and there's there's fire ants, and there's bees, and there's these various species of mosquitoes, and grass, and dirt, and intestinal worms. It doesn't know these things, ahead of time. It has to be exposed to these things. So ultimately, how does a baby get exposed to these things? Well, first introduction is through the birth canal. Welcome to the world. You get access to all that stuff. Same thing through the mother's skin while the baby's breastfeeding, and also just directly through the milk with antibodies. That's how it's getting some sort of exposure to this is what the world around you is like, so to get used to it and normalize to that or adjust to that. But also by literally putting everything in their mouth. If you see a little baby moving around, they're not just there to make you anxious and paranoid all the time. They're doing that because ultimately that's how their immune system is going to know what's out there in the world. They can't just look and see grass through your eyes. You have to actually taste that, touch that in there, so your immune system can make that sort of chemical handshake and say, oh, okay, this is part of the normal world. Let's go ahead and ignore that in the future. So again, that's part of why babies literally put everything in their mouths as they're sampling this environment, which is crucial information. Because if mosquitoes are part of your normal environment, if pollen from certain plants are part of your normal environment, if dogs are part of your normal environment, if grass is part of your normal environment, then your body should basically ignore those things and put them on the tolerate and ignore list. Compared to things that actually might be introduced later on that might be harmful, that are kind of disrupting that norm. So what happens if you take a baby and you raise it in a sterile environment? You put it inside, it has these really awesome air filters so nothing can get through, and again, it's a sterile room, doesn't get exposed to animals. What does that baby's immune system make? What assumptions is it making long-term about its life when it's developing this sort of immune system architecture? What assumptions is it making? It's assuming that this is normal. And so not only, it's assuming two things. Not only is your environment basically have not a whole lot of things that you're probably going to be exposed to in a quick hurry in a few years when you start going outside and really get out there regularly. And it's also not exposing your body to enough sort of dangers and stresses. And just like growing up, if you're growing up sheltered without stresses, you don't know how to appropriately respond when things go wrong, compared to if you grew up in much more stressful encounters, then you can kind of handle that a little better. So the idea is if your immune system is never really challenged much early on, then even when the smallest perturbance happens, your immune system might just kind of freak out. So that's what you're basically exposing this baby to or setting up for the rest of its life. So this sort of mismatch of what your immune system's sort of looking out for versus what it's been exposed to and then what it's later exposed to in its life, we refer to that sort of mismatch as the hygiene hypothesis. And that's this notion that a lot of this immune system dysfunction and recognizing what things are actually dangerous versus not dangerous, and also its magnitude of response, these are all kind of under this umbrella of this notion of the hygiene hypothesis, saying that these immune system dysfunction are immediately related or caused by this lack of exposure when you're young. So sanitation, fantastic for reducing the spread of disease, and so on and so forth. But you can clearly see that sanitation taken to the extreme could actually now set your immune system up to not develop properly. So there's a few lines of evidence that support this notion of the hygiene hypothesis. And the first is that you tend to find that immune system dysfunction are associated with urban living or modern sort of living. Now, this is not to say that urban environments and metro centers are clean by any stretch of the imagination. It's just saying that they're less natural. So you're not going to get exposed to as many plants, animals, and so on and so forth than you would if you lived out in sort of, urban outskirts, suburbs, and the rural areas. So when we look at things like allergy rates, and allergies are your body responding negatively or responding adversely to something that is actually not harmful to you. If you have allergies to pollen, there's nothing dangerous about pollen. It's that your body didn't put that on the ignore list, so therefore it thinks of it as an invader. It's something that's disrupting the normal for you. You think of cats and dogs. They're not inherently dangerous to you chemically, but ultimately your body wasn't exposed to this. It goes, what is this abnormal feature of my environment, and can respond harshly to that. And even think about things like peanut allergies, which are extremely harmful to individuals. And you go, well, what's dangerous about a peanut? Well, ultimately, there is nothing dangerous about a peanut. The problem is your body, if you have an allergy to peanuts, it just can't or didn't effectively tell the difference between a peanut and an intestinal worm. And I know they are completely different things, but again, how your immune system identifies things, it identifies them by their chemical signature. And if the proteins it just so happens to identify species of hookworms with are very similar to proteins that are on peanuts, well, then your body might mistake one for the other if it hasn't seen one or the other. So that is, so again, a lack of exposure. And that's also why peanut allergies really highlight the two issues here. One, it's mistaking peanuts for an intestinal worm, and two, its response is so exaggerated that it's actually detrimental to you as the individual. So it's not the peanut that killed you, it's your response to the peanut that killed you. So anyway, these sort of misfirings, these allergies, misfirings are more common as you increase in population density. So you could see that the allergy rates are the lowest in rural areas, but gradually start increasing stepwise, essentially, to urban outskirts, to suburbs, to urban outskirts, to urban areas, and then the metro centers. Now another area where you kind of see this sort of modern environment being included in are with our actual exposure to intestinal worms. You don't really think of humans really kind of having intestinal worms as a normal thing, but basically every animal that's running around out there has some sort of intestinal parasite sort of plaguing it. And their body has to essentially get used to it or deal with it somehow. And humans were not the exception there. So there is a common parasite that co-evolved with humans called the whipworm. It's basically in the soils of anywhere that doesn't completely sort of freeze over. So it's really common. It occurs sympatrically with humans across the world, except for, again, the extreme sort of latitudes near the poles. And again, it closely overlapped with our range in our early evolution as well. And these whipworms, now, the eggs are all in the soil, it's defecated out in the animal. And what happens when you get these whipworms, just from eating dirt, you just get it. You eat plants, potatoes, whatever, these tubers, things you're ripping out of the ground, you're going to end up getting this stuff. But it's not a multi-generational parasite. It means it's not having multiple generations inside of your body. It's not a persistent infection. It's not chronic. So you get this whipworm egg, it hatches to an adult, reproduces, and the little eggs just go right on out to go get something else outside. When those adult population die, that's it, it's out of your body. You don't have to deal with it anymore. But your immune system still kind of got exposure. So you can imagine how many little ones we're immediately exposed to this early on in life while you're just kind of crawling around. And humans they don't show symptoms of this unless you have hundreds of them literally inside of your body. So it's probably assumed that overwhelming majority of humans were exposed to this. And now, because of the modern environment, we're not really being exposed to these things nearly as much. And there's a really awesome sort of figure that shows the comparison of where you find these intestinal worm infections and where you find autoimmune disorders, and they're the complete sort of opposite of each other. So in these countries where you have, again, less essentially modernization and warmer climates, but more exposure to these whipworms, you also coincidentally have less occurrences of immune system related disorders, and as well as inflammatory bowel disease. Essentially, if you're not being exposed to these intestinal parasites and your immune system's kind of waiting for something to show up, something might show up similar enough to it that, again, it might misfire and go after that. And that is why, again, the association between inflammatory bowel diseases are also strongly associated with increased urbanization. Now, another line of evidence supporting the hygiene hypothesis are actually based on this notion of the old friends hypothesis, and that is kind of a clever one. It's very similar to the hygiene hypothesis. The idea is that your immune system co-evolved with various other species. And these might be beneficial, they might just be neutral, and they might be harmful. So the old friends hypothesis simply says that we co-evolved with these old friends. And again, these improvements in sanitation and lack of exposure to the natural environment can potentially increase these developmental disorders in the immune system because, again, this lack of exposure to old friends. So one line of evidence supporting, again, the hygiene hypothesis is simply suggesting, what if we just re-expose individuals to these old friends? Can that provide some sort of treatment, maybe re-education of your immune system, albeit later on? Well, that's actually been attempted using intestinal parasites, intestinal worms. They call it Helminth therapy. Helminth is referring to that group of intestinal worms. So the idea here is, if individuals have these sort of misbehaving immune systems, if we give them essentially what they were intended to go after, will it sort of leave everything else alone? Will it readjust its aim and kind of and go back to what it's supposed to be doing in the first place? So they investigated this association with reintroduction of these old friends and reduction in symptoms of individuals suffering from Crohn's disease. So Crohn's disease, it's an inflammatory bowel disease. It's basically, again, just defined as extreme inflammation of your guts just in response to things that aren't necessarily harmful. So treatments for that usually involve immune suppressants or anti-inflammatories. So the idea here is that maybe individuals are expressing Crohn's disease because their immune system wasn't given exposure to maybe intestinal worms. So now it's making this wrong sort of connection. It's attacking the wrong things, and it's also attacking them more severely than it would normally as well. So they brought in participants. They had Crohn's disease, and they assessed them based on their CDAI score, or they assessed them for their CDAI score, and that is the Crohn's Disease Activity Index. So if you're above 150, you have Crohn's disease. The average participant was around 300 for their CDAI score. And what they did for their treatment was they just simply said, okay, consume these whipworm eggs. And it might sound horrible at first, but they used pig whipworm eggs. So these whipworm eggs won't actually hatch inside of a person. They'll just pass right on through, but the immune system can kind of go, wait, what was that? And respond appropriately. So therefore, when you finish the study, you don't have any parting gifts along with you. And they're microscopic, you can't taste them. They just mixed it in with, I think, Gatorade and delivered it to individuals. So they just kind of continuously consume this stuff throughout a few week span, or over the course of many weeks, actually. And what they found was very quickly, actually, I believe after only a few months, that these individuals had an incredible relief of their symptoms, where the average CDAI score after just a few months went to under what would actually be considered an individual with Crohn's disease. So it was under that 150 threshold. So just by reintroducing this sort of old friends, and only partly, when it's just an egg just kind of zooming on through, even that had an extremely potent effect on relieving the symptoms of Crohn's disease by reducing the CDAI score. And it's not surprising that Hellman's therapy are being applied to many, many, many other topics. There's case studies currently involving Hellman's therapy with multiple sclerosis, which again is another immune system dysfunction. Your immune system is attacking parts of your nerves. You have it also applied to things like colitis, which is another inflammatory bowel disease, things like asthma, and it's again many other autoimmune or immune system related sort of dysfunction that it's being applied to. Now, the last topic, or the last example I want to use with regards to this applying this old friends hypothesis is actually with type 1 diabetes. Type 1 diabetes is different from type 2 diabetes. The symptoms are similar. The cells in your pancreas that normally produce insulin aren't doing that anymore. In type 2 diabetes, it's because they've been fatigued. As you accumulate fat, your body becomes resistant to insulin, because insulin is what tells the cells to take in sugar and fat from the bloodstream. So the more fat you have, the more your body goes, no, I don't want to deal with this. So ultimately, the cells that are producing insulin just become exhausted. With type 1 diabetes, it's actually a different ballgame how you lose those cells. What happens is at some point in time, your immune system decides that those cells that are producing insulin are actually enemies, and they attack and destroy them, and now you're not producing insulin. So two different sort of causes, same kind of poor outcome. So why? Why would your immune system just go and start attacking these pancreas cells when they didn't do anything? Well, it's because, again, it just misfired. It couldn't tell the difference between friend and foe, especially if it hasn't had exposure to them before. So it turns out that what your body is actually using to identify an attack is this protein. It's called a heat shock protein, and it's expressed on those insulin-producing cells when they're stressed out. So if you became sick, got the flu or what have you, and those cells become very, very, very stressed, they might start producing this protein. That's why your immune system doesn't attack them, day number one. But it turns out that there's a bacterial pathogen that expresses a very, very similar protein, almost identical. So when that is expressed, that's what your body looks at and goes, okay, that's how we know we have that bacterial pathogen. But if it wasn't exposed to that, then it might, again, misfire and attack your insulin-producing cells. So that obviously begs the question, what if we expose individuals to that bacteria, maybe a non-pathogenic form of it, a friendly form of it, so your body goes, oh, okay, I see what that is. And then when it sees your body in a potential situation where it would be expressing that heat shock protein, it goes, oh, no, don't worry about that, it's fine. Now, that's actually been investigated in the 90s, no less. So they investigated this in rodents. What happened is they found this line of rats that were, kind of predisposed to developing type 1 diabetes. And they looked inside their blood to see when they started sort of having this heightened immune response, basically when they were about to start getting full-blown type 1 diabetes and just annihilate their own cells. So at that moment, they injected them with either saline, so basically nothing as a control, or with these bacteria, these friendly bacteria. So again, enough to, again, alert the immune system or educate the immune system. Well, the ones that were injected with just salt water, saline, went on to develop type 1 diabetes. The ones that were injected with the bacteria did not actually go on to develop type 1 diabetes. And if you actually inject some with that bacteria and also inject them with an immune suppressant, they actually eventually go on to develop type 1 diabetes, because what happened is, you injected them with what the immune system wants to look at, but you suppress the ability to look at it, so ultimately you never learn from it. So it's kind of a back confirmation of that. So really, really clever design. So they obviously said that this should be used for, considered for human testing. Now, obviously, testing a new type of vaccine, which this would be a vaccine for type 1 diabetes, has some dangers. What are the long-term effects of this? Well, that would normally apply. However, the substance they used, this vaccine that they used in these rodent trials, is actually the BCG vaccine, which is a vaccine that is used to stop tuberculosis, TB. So ultimately, this is something that's already been exposed to humans. We already know the long-term consequences of this. You just got to inject it somewhere else. But lo and behold, the trials are really taking a long time. But it should, again, be just a remarkable discovery, and essentially vaccine against one of these sort of modern ailments. And again, inspired from an evolutionary perspective. Now, one last thing I wanted to really talk about is what can we do in our daily lives that maybe to try to facilitate this, or to try to circumvent, go against some of these nasty issues of these mismatches, or develop a proper immune system. Well, there's been a few cool studies that have highlighted just minor changes in child's life, or in an infant's life, that have profound impacts on the development of the immune system. The first is they actually looked at how pacifiers are cleaned, and how that can affect, again, immune system issues, or the development of immune system issues. So there's basically two camps when it comes to cleaning a pacifier, the baby's pacifier. There's some parents where it falls on the ground and they go, oh, no, we got to sterilize this, and they boil it and do whatever they can, and then put it back in their offspring's mouth. And there's other ones that just go, oh, it fell on the ground, they kind of just dust it off, lick it themselves, and then just go, oh, here we go, and put it right back in their offspring's face. Now, one of them is sterile, and the other one is obviously going to expose the baby to potentially whatever's on the ground and whatever was in your mouth, which is whatever you had to deal with for the last day or so, whenever you just ate, and so on and so forth. So these researchers asked these new parents, what are you going to do when the pacifier falls on the ground? And if whatever camp they fell in, they go, can you just do that reliably for the foreseeable future? And they're like, yeah, sure. So they had these two camps, essentially, and then they had a control group. And they later compared, a few months later, upwards over a year later, the eczema rates of these individuals, the rates of them developing asthma, and as well as sensitization rates, which is basically just a heightened sort of immune system where it's kind of, on a high state of alertness. Not a good thing necessarily. So what they found is that individuals whose parents just dusted off the pacifier and licked it and gave it to the infants had significantly lower rates of eczema, asthma, and sensitization than the other ones. And that's just based on pacifier use. Another interesting finding was just growing up with a dog in the house. And it's not that you're just going to become tolerant of dogs, which obviously you imagine you would become tolerant of dogs if you're exposed to it very early on. But if this dog is also an outdoor dog, and it can run around out there and get all this sort of interactions with the outside world, then come right inside and just dump that on your face from their fur and licking you and so on and so forth, then they're serving as a proxy, sort of that outside environment. So again, small little subtle things can have huge impacts when it comes to how, again, the body is developing. So just things to keep in mind. So again, to just rehash, evolutionary medicine, Darwinian medicine is really just applying this sort of why thinking to the field of healthcare and understanding our understanding of disease. And it really, again, boils down to the lack of appreciation of evolution contributing to the fact that symptoms are often adaptations. We are often engaged in evolutionary arms races when we're trying to treat disease, and we have strong mismatches for our environment. Although it might be unpleasant to think about and very difficult to counteract, like things like obesity, it's something that we have to essentially be mindful of. That's all.